morning. I am Dr.K.ELAYA, working as Assistant Professor in Department of Physics, St.Joseph College of Arts and Science, Cuddalore. Today I am going to explain the topics on mechanics of a particle. Comes under the subject classical mechanics. So today I would like to explain the conservation of linear momentum and the conservation of angular momentum. So we know the formula for a linear momentum. So mentioned by letter P, P equal to mass into velocity. So we can change the linear momentum with radius, then it comes under the angular momentum, which means once the particles moves in a straight line, we call this a linear momentum. On the other side, the particle moves in a rotational motion or a circular motion, then it possesses a momentum named as angular momentum. So this is the basic difference between linear momentum and angular momentum. So how we conserve the linear momentum? So where we start the concept of linear momentum, and also for angular momentum, how we conserve, how we correlate with the another physical terms. So now we start with the conservation of linear momentum. So linear momentum, we start with this from Newton's second law of motions. We know about the three Newton's law: first law, second law, and third law. So first law we can state this: the particle continuously moves in straight line unless otherwise it is disturbed by any other external force. The second law only F equal to mass into acceleration. So others we can call this F equal to dt by dt. In this P which represents the linear momentum. So we can write the equations from Newton's second law of mechanics. D of mv by dt we call or we write as dp by dt, which is equal to force. So force equal to dp by dt, or otherwise called as F equal to mass into acceleration. So from the mass into acceleration only we can derive this answer dp by dt. Now we consider there is no force acting on the particular particle, which means F equal to 0, automatically dp by dt also equal to 0. Once the F equal to 0, dp by dt also equal to 0. Since F which is equal to dp by dt. So as per mass, differentiation of any constant, we get the answer 0. Differentiation of any constant value, we get the answer 0. So in this equation, instead of a constant, we get dp by dt, which indirectly shows what? Linear momentum is constant. Linear momentum, V which indicates linear momentum. Linear momentum is constant. It shows that now linear momentum is conserved. So now we concluded that we can conserve the linear momentum from Newton's second law of mechanics. So first of all, conservation of linear momentum, dp by dt equal to 0, which means the P will become the constant. So we can conserve the linear momentum. Next, second one, conservation of angular momentum. The angular momentum, you may tell us L equal to R into P. Angular momentum L. Angular momentum is denoted by capital L, which is equal to R into P, which means we can product the linear momentum with the radius, then we can get the answer angular momentum. This equation indirectly shows that the object moves in a circular path, since we can include that radius on. So L equal to R into P. We know the F is nothing but a force acting on the particle. Then we can write the tau answer. Tau is not the torque acting on the particles. We know the torque. So radius into force, R into force, which resembles the tau value. So from this equation, we can substitute the F value, which is equal to dP by dt. Now, with the help of mathematical integration, vector cross product, we may write this equation as d by dt of R into P minus dR by dt into P. Then we can simplify this equation. We know velocity equal to distance by time. So dr by dt is the distance by time. We write this equation as B. We know the value for P. P equal to mass into velocity, linear momentum. P equal to mass into velocity, m into v. Now this will become to 0. Once these two terms are in parallel position, we can calculate this term into 0. So we cannot bother about the second term. Now it becomes a 0. So rewrite this equation as tau equal to d by dt of R into P. So R into P, which is equal to, we already written L. So instead of R comma P, here we substitute dL by dt. So now we have to consider the angular momentum. So we can equate this tau, which is equal to 0, which means dL by dt also becomes 0. So once the tau is 0, dL by dt also becomes 0. So which indirectly resembles that L will become a constant. So constant means now the angular momentum is conserved. So L is the angular momentum which now conserved. From the above equation we can conclude the angular momentum is conserved. So we can conclude it from the L equal to R into P with the help of torque equation. For the first one, linear momentum, we can conclude that it is conserved from the Newton's second law of mechanics. Okay, thank you.